Hi, I'm Herb Gross, and welcome once again to our Math as a Second Language video series, where today we're going to be discussing decimals. And I hope you've noticed that up until now, we could have called all these lectures Find the Decimal Point, Locate the Decimal Point. Everything has been exactly the same as whole number arithmetic, except for where do we put the decimal point. And we were using the adjective noun theme to justify why the decimal point goes where it does. So to be consistent, we're going to do exactly the same thing now. We're going to show that once you can locate where the decimal point goes, when you divide two decimals, you divide them the same as if they were whole numbers, okay? Let me start with a whole number problem, which I don't think should be too difficult to get started with. Suppose I say, and this could be as early as what, third grade? 300 divided by 4. It's what the kids call Gazinta problems. 4 goes into 300 75 times. They do something like this. And so they know that 300 divided by 4 is 75. But keep in mind, these are just the adjectives. As adjectives, when you divide 300 by 4, the adjective answer will always be 75. But what that 75 modifies depends on what the 300 and the 4 modify. So suppose the 300 was modifying apples, okay? And you're going to divide the 300 apples into 4 equal piles, okay? So now the problem is 300 apples divided by 4. How do you do that? You're still going to divide the two adjectives. You're still going to do this part of the problem. The only difference now is that after the 300, you're going to put the word apples in, and up on top here after the 75, you're going to put in the word apples. In other words, the quotient stays the same as far as the adjectives are concerned. Now, what if the noun was hundredths? 300 hundredths divided by 4. You're still going to divide the 300 by the 4, but now the answer is going to be modifying hundredths. So what you're saying is that 300 hundredths divided by 4 is 75 hundredths. Now let's translate this now into the language of decimals. To get rid of the word hundredths, what do I have to do? Hundredths indicates that there are 2 digits to the right of the decimal point. So I have to remove hundredths, I have to move the decimal point in 2 places to the left. See, notice the tricky wording here. I have to move the decimal point 2 places to the left in order to have 2 digits to the right of the decimal point. So 75 hundredths becomes 0.75. 300 hundredths becomes 3.00. And hence the mechanical rule that to divide 3 by 4, okay, sorry about that, you put in 2 digits to the right of the decimal point, you line the decimal point up, and then divide as if the decimal point wasn't there. See, that's the logic behind the mechanical rule. In other words, as long as the divisor, that means this number, as long as the divisor is a whole number, all you have to do using the division algorithm is line the decimal point up so that the decimal point here matches up with the decimal point here, and then divide as if the decimal point wasn't there. So for example, just like I did this, suppose we wanted to write 7/8 as a decimal. What you do is, we're not going to divide the 8 into 7. Well, we are, but in a clever way. See, 7 is the same as 70 tenths. It's the same as 700 hundredths. It's the same as 7,000 thousandths, etc. So I line up the decimal points and do the division. 8 goes into 70 8 times the remainder of 6. 8 goes into 67 times the remainder of 4. 8 goes into 45 times with no remainder. By the way, I don't have to stop here. It's just that what's going to happen from here in? There's just going to be zeros. And putting zeros to the right of the digit, of the non-zero digit that's furthest to the right, doesn't change the number at all. See, all these are maintained in the same place. How would I write this number as a fraction? Without the decimal point, I see 875. There are 3 digits to the right of the decimal point, so I want 3 zeros to the right of the 1 over here. And what that says is this would be 875 over 1,000, which doesn't look like 7/8, but watch what happens. See, remember, 1,000 is what? It's 10 times 10 times 10, which is the same as 2 times 5 times 2 times 5 times 2 times 5. What happens to 875 if I break it down into prime factors? If I divide 875 by 5, the answer is 175. 175 is divisible by 5. The answer is 35. 35 is divisible by 5. The answer is 7. So 875 is 5 times 5 times 5 times 7. And now notice what happens. We can cancel common factors. On top is left a 7. On the bottom is left 2 times 2 times 2, which is 8. And that checks out with being the right answer. Okay? So as long as I'm dividing, doesn't matter what this decimal is. As long as this is a whole number, I simply put the whole number out here, whole number, the decimals in here, and I line up the decimal points, and I'm off and running. Now, without belittling the importance of being able to compute accurately, the real beauty of mathematics, the part of mathematics that every student should be able to carry with them once they finish the mathematics curriculum, is the power of logical thinking. For example, in this particular case, we now know how to do any division problem involving decimals, provided that the divisor is a whole number. Well, in the real world, the divisor might not be a whole number. Look, for example, at, say, 0.02 divided by 0.0004. Now, I was taught how to do this in school. I had no idea why it worked. See, what they said to me in school was, oh, look, don't worry about this. You can make this a whole number. All you have to do, and it's simple, all you have to do is move the decimal point 4 places here, and that will make this a whole number. And then you do the same thing in here, move the decimal point 4 places. Well, there's only 2 places, so I'll put in 2 zeros. And now they say, pretend that this is where the decimal point is now, and do the problem as if the decimal points weren't there. Just line them up. And I'm thoroughly confused because I get this decimal point mixed up with this one with this one, this one with this one. Here's what I want you to see. The logic of this is simple if I use what we've learned before. What we already know is how to solve this problem if the 0.0004 had been a whole number. The problem is it's not a whole number. So the trick is, how can we make it into a whole number without changing the meaning of this problem? Well, one way to make this into a whole number is to just move the decimal point 4 places to the right. You can say to yourself, gee, you know something? If the decimal point had been over here, this would have been easy. Well, the problem is the decimal point isn't there. You say, well, what would happen if I moved it there? Well, I have to move it 4 places to the right. Every time I move the decimal point 1 place to the right, I'm multiplying by 10. So I've multiplied by 10 once, by 10 twice, by 10 3 times, by 10 4 times. I can do that, but now I've changed the answer. Provided, if I can now do something to offset that, I'll be all right. Well, what do we know in a ratio when you divide? If you multiply both numbers in the rate by the same number, you haven't changed the value of the ratio. So what did I do over here? I multiplied by 10 4 times. What am I going to do over here? I'm going to multiply by 10 4 times. If I do that, 0.0004 becomes 4, and 0.02 becomes, I'm moving it 4 places, move it 2 places, I still need 2 more places, I have to tack on 2 zeros, so the problem becomes 200 divided by 4, which is 50. Notice that that's exactly what happened over here, only we made it sound like magic. You said, move the decimal point 4 places here, Now move the decimal point 4 places here, and now forget that there's a decimal problem. Well, this shows you why. All you were really doing when you said move the decimal point 4 places here and move it 4 places here is that you were multiplying both numbers by 10,000. See, 1, 2, 3, 4, 4, 0. 1, 2, 3, 4, 1, 2, 3, 4. By the way, to check that this is right, people say, how can you have two such small numbers giving such a big answer? And what's really happened over here is that what you're saying is 0.0004 is a small number, and 0.02 is a small number, but compared to 0.0004, 0.00200 is 50 times as big. In other words, how would you multiply these two numbers? Our rule for multiplication is what? Multiply as if the decimal points weren't there. 50 times 4 would be 200. Count the total number of digits to the right of the decimal point. There are none here. There are 4 here. So move the decimal point 4 places. And there's the answer. In other words, what did we do here? Even though the divisor wasn't a whole number, there was a mathematically correct way of converting it into a whole number by doing something to it and the similar thing to the other number, and then we were able to convert a problem that we didn't know how to solve into an equivalent problem that we did know how to solve, okay? I think, let me just do a couple of more examples, not working them out, but showing you what I mean. Here's a particular problem where we're dividing two decimals. What would it take to make this a whole number? Well, I would have to move the decimal point 6 places. That's multiplying by 10 6 times. To keep the rate the same, I would have to move the decimal point here by 6 places. But there are only 5 digits here. So to move it 6 places, I would have to tack on a 0. Psychologically, doesn't this problem look less threatening than this problem? In other words, I don't have to worry about dividing these two decimals. All I can have to do is look at this as a whole number problem. Doesn't matter. Doesn't matter where the more digits are, whether it's in the divisor or whether it's in the dividend. Suppose the problem had been 0.003286 divided by 0.05. To make this into a whole number, I would only have to move the decimal point 2 places. But if I move the decimal point 2 places here, I have to move it 2 places here. But if I move the decimal point 2 places here, I still have a decimal. That's no big deal because as long as this is a whole number, I can divide the way I did before. But if I don't want to deal with decimals at all, I say, look at, if I move the decimal point 6 places here, I will get a whole number. What number will I get? 3,286. But if I move the decimal point 6 places here, I have to move it 6 places here. There's only 2 digits. I said, yeah. So I have to tack on, say I moved it 1, 2, 3, 4, 5, 6. I have to move it 1, 2, 3, 4, 5, 6. Okay? And so the problem becomes what? 3,286 divided by 50,000. Again, all you have to do when you're dividing two decimals is to see the least number of places where you have to move the decimal point so that both of the numbers become whole numbers, and you can do that just as we did over here. But there is a fly in the ointment. See, over here we said what? Count the total number of digits to the right of the decimal point. What happens is, in some division problems, there won't be a digit furthest to the right. Suppose you were to look at 1/3, 1 divided by 3. 3 goes into 10 3 times with a remainder of 1. 3 goes into 10 3 times with a remainder of 1. 3 goes into 10 3 times with a remainder of 1. This is going to go on forever. And since the sequence of 3 never ends, there can't be a last digit. Up until now, we've done everything in terms of saying, let's see how far out we have to go to make this into a whole number. Now we see an example where here's a decimal that never comes to an end. So I simply say, stay tuned, which means that this is something we're going to be tackling in a future lecture. So for now, I think this is a good place to stop. to make sure that you understand the idea of what division really means. Namely, it will always tell you the relative size of two numbers. We don't usually teach it that way. We simply mechanically will say something like 6 divided by 2 is 3. What it really says is, I don't know whether 6 is a big number or a small number, but compared to 2, it's 3 times as great. Okay? That's what division really means. That's the way I want students to understand it, and you to understand it. And I think that with that as a closing remark, let's go to our practice problem, which today is when we divide 0.0001 by 0.000001, the quotient is 1,000. Explain how the quotient of two such small numbers can be equal to 1,000. So just pause the video, work out the problem. When you have an answer that you're satisfied with, resume watching and see how your solution counters or works with mine, and we'll take it from there, okay? You know, in analyzing this problem, it reminds me of a bumper sticker. It's a rear bumper sticker that always amused me. The rear bumper sticker said, "I may be slow, but I'm still ahead of you." And I thought that was kind of humorous. You say, well, that's funny, but what's that got to do with this problem? Well, let's take a look at 0.0001 divided by 0.000001. We want to make this into a whole number, okay? To do that, we have to move the decimal point 7 places to the right. That means we have to move it 7 places to the right over here, but there are only 4 digits to the right, so we have to tack on 3 more zeros. So if we take this amount this many times to bring it up to 1 and do the same thing over here, the problem becomes the same as what? 1,000 divided by 1, which is 1,000. And so what this is really saying is 0.0001 is saying to 0.000001, I may be small, but I'm still 1,000 times bigger than you. And to check that, let's see what happens. If I multiply 1,000 by 0.000001, I multiply as if the decimal points weren't there, and that would give me 1,000. But then I have to move the decimal point. Let's see, there are no digits to the right here. There are 7 over here. So I have to move the decimal point 7 places to the left. There are only 4 digits here, so I have to put in 3 more zeros here. I do not need these zeros because they come after the digit furthest, the non-zero digit furthest to the right. And so lo and behold, the answer is 0.0001. In other words, as small as this number is, it takes 1,000 of these guys to equal that one. And I think that brings us to a nice place to close for today. I'm looking forward to continuing our discussion next time. And until next time, have fun, stay young.